Alright, 7.3 video notes. Title of the section is Indirect Measurement. Basically, we're going to be using the proportions that we set up earlier to solve some real-life type of problems. And indirect measurement, let me just go full screen here. Indirect measurement is basically a way to measure the height of something without actually climbing up to the top of it and holding a tape measure or using some other electronic way of measuring. Is to kind of go old school and use shadows and things of that nature. So we're going to try to set up some similar triangles on these problems, and it should allow us to find the height of things that we may not know. So let's look at the first problem here. It says a 150-foot tall building casts a shadow of 225 feet. How many feet tall is a nearby building that casts a 75-foot shadow? So basically you're going to draw the ground, and I'm going to do the first building here in blue. So 150-foot tall building, and don't waste a lot of time on your drawing, just kind of put a building like that. So that's 150 feet tall. Casts a shadow of 225 feet. So the shadow is going to actually be here on the ground. So it's got to be a sunny day outside. And we'll pretend the sun is up here somewhere, casting a shadow, and it kind of comes down and clips this corner and comes down, and then you see the shadow on the ground. So the shadow is 225 feet. So we knew the height of this building, and it obviously has to be a sunny day in order for this to work. So then you have another building that has a 75-foot shadow. So a smaller shadow, I'm going to assume that it's a smaller building. So you have this small building right here. And the whole key to why this problem works, and the way I've drawn it, it doesn't look like it would be true, but the sun is 93 million miles away. So basically the angle up here at the top coming down for both of these buildings should be similar to each other. They might be 1,000th of a degree off or something like that, but for all practical purposes, that angle is the same. And so we have the right angle at the bottom, we have the same angle at the top, which means we're going to have, by the third angle theorem, the same at the bottom. So I know they're the same shape and they're similar. Now my second picture, I know the shadow. I can measure that from the ground, so I can measure the shadow here as 75 feet. And I'm trying to find h, or x, or whatever you want to call it. I'm trying to find the height. So it's just like what we did with triangles. Now we just put it into a word problem. So I'm going to set up a proportion. And it doesn't really matter how you do it. You could do height over shadow equals height over shadow. So let's just look at that one. The big building's height over the big building's shadow equals the little building's height over the little building's shadow. Some people like to use corresponding parts, and they'll do big height over little height, and then big shadow over little shadow. And even though you have a different proportion, when you cross multiply, you're still going to have 225h, regardless of which way you go. And then you're still going to have 75 times 150. So let's just put that in here, 75 times 150. And that's 11,250. And now I use my algebra. I divide both sides and divide both sides. And I figure out that the height is 50 feet. And then I always want to look back at the picture and just ask myself, does that make sense? And this one actually probably would have been easier to use a scale factor. If I kind of use a scale factor, and I would have noticed that this is exactly 3 times larger, I could have also known that this was going to be 3 times larger, or 3 times smaller, because I was going in the smaller direction. So there's other ways to do it. If you prefer scale factor, you could use that method as well. But that works nice for when it's a overcast day, or not an overcast, a sunny day. You could use shadows. So let's move on down to the next problem. An 18-foot tree casts a shadow of 9 feet. Now I notice right away these numbers are pretty nice. So I have a tree that is 18 feet. I have a shadow which is 9. So right away those two numbers jump out at me that I see a 2-to-1 relationship between the height is twice as long as the shadow. So I should be able to use that for the next part. It says, how long will the shadow be of a person? So you have a person standing here that we know to be 6 feet tall. And so we're trying to find the shadow on this one. So you could set up a proportion. You know, I could do tree height over tree shadow equals person height over person shadow. But I also can see, you know, a couple different things. One is that the shadow is half of the height. That would give me the answer. I could also use scale factor and see that the tree is 3 times larger than the person, so the shadow should be 3 times smaller. I mean, there's a lot of different ways to do it. Or if you don't really like doing that and you just like to use the old mechanical solve proportions with cross products, you could do that as well. And either way, you're going to find out that the shadow is 3. Alright, so very similar to the building one. Now, coming down here on the bottom, this one's a little bit different. A ladder is 30 foot tall, leans 25 feet against the side of a building. So let's kind of draw that down here. I'd start with the ground, and I have some building, and then I'm going to lean a ladder up to it. There's the ladder. And it's a 30 foot tall ladder, so the red or the blue there is 30. It leans 25 feet up against the side of a building. So it reaches a height right here of 25 feet. Up against the same building, how far up would a 20-foot ladder go? So a 20-foot ladder, and we're going to assume that the angle is the same. There's usually a safety standard for the steepest angle that you can have a ladder go up to, and it usually has that printed on the ladder. But I'm going to just draw it in like this. So we have a 20-foot ladder, and then we need to find this little height for just this piece. And if you prefer, you could separate those two. You know, just basically draw triangles. You don't have to redraw the whole building, but 30-foot ladder goes up 25, 20-foot ladder goes up how much, and depending on how you want to do the proportion, I'll do corresponding sides on this one. A 30-foot ladder, so big ladder over little ladder, equals big height over little height. That would work. Again, lots of different ways to set that up, but when you do it, you should get 500 equals 30x. Divide both of these by 30, and you will find 50 divided by 30 is 50 over 3, which 3 goes into 50, 16 2/3, or 16.6 repeating feet. Now, if I wanted inches, 2/3 of a foot, well, that's 2/3 of 12, because there's 12 inches in a feet, and that would come out to be 8 inches. So the final answer in inches would be 16 feet, 8 inches. Sometimes on standardized tests they don't want decimal feet, they want inches. So whenever you have a fraction or a decimal, the key is times by 12 inches. Alright, if you have a decimal or a fraction of feet, just times it by 12 and it'll hook you up with the inches. If you want to go the other way, if you know the inches, you can divide by 12 and get the decimal or the fraction. Alright, moving right along. Number 4, two-part question. A 9-foot tall stop sign casts a shadow of 12 feet. So if you really want to, you could draw a stop sign, but I'm just going to put this here and put some goofy thing on the top like that. A 9-foot tall stop sign, 12-foot shadow, and a building near this by has a 63-foot shadow, so I can't really draw this to scale, but I'll kind of somewhat try to make it similar. So 63-foot shadow, and I would need to figure out how tall is the building, so find h. So again, same thing as before. I'm going to do little height over little shadow equals the bigger height over the bigger shadow, and I will get 12H equals, that's 540 and 27, 567, and divide both sides by 12. And let's just put that in the old calculator and see what it shakes out. 567 divided by 12 equals, punch something in wrong, 47.25 feet. That's decimal feet. Now if I wanted to change this into inches, I go 0.25 times 12, and a quarter of 12 would be 3 inches. So 47 feet, 3 inches would be the exact height of that building. Now, the second part is this. It says, if the distance from the top of the building to the end of the shadow is 87 feet, so we're talking up here, the distance from the top of the building to the end of the shadow on the ground is 87 feet. If that's the case, how far is the distance from the top of the stop sign over? So we'll just call this X. And I can use the same idea I did before, just with another proportion. 9 is to not 12 this time. I can do whatever dimension I want, but I'm going to do height and length. Height over length equals the height here, which was 47.25 over 87. So basically I did height over length, height over length. Probably wasn't the best move. I don't really recommend that, because if I make a mistake here and that answer's wrong, it's going to force part B to be wrong. So I'm going to go back now that I see that, and I'm going to correct this a little bit. I'm going to go back and change this. I'm going to use the bottom. Whoa, didn't want to do that. I'm going to use this bottom dimension. I'm going to use the bottom over the distance and the bottom over the distance. That way I know that I didn't make any mistakes. These were numbers that were given to me, with the exception of 87. But no, they give that to me too. So all these three numbers were things that were given and I didn't have to calculate. So my chance of screwing it up is a little bit less. So now we're going to crank this out. I got 87 times 12. Boom. 1044. And divide both sides by 63. And boom. I get about 16.571 blah 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 blah. So this is feet. So I know this is 16 feet, and then again, if I want to change it into inches, I take this portion of it and I multiply by 12. So I'm going to do 0.5714 blah 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 times 12, and it comes out to be about 16 feet and almost 7 inches. If I was going to round it, it would be 7 inches. It was actually 6.8 inches. But it all depends on the test. Do they want just your decimal feet, or do they actually want inches? It doesn't really say so, but be prepared to be able to do both. The big thing I want you to know is, if the answer is like 6.3 feet, that does not equal 6 feet 3 inches. That is the most common mistake, and that is just not true. All right, so you can't just look at the decimal and write it down as inches. It doesn't work that way. It'd be nice, but it doesn't. All right, final question. I put this on here, and this kind of inspired me by my one of my teachers in school. We had a park down the road, and he had told us all about how we were going to measure the height. There was we had a sister city, was some city in Japan. I don't even remember the name of it now. I want to say like Nagasaki or something like that. But we had a sister city, so we had this park that had like some monuments from that city, and we were going to go and measure the height of the monuments using shadows. Well, we were walking down there that day, and it was overcast, so the whole way down there I'm kind of like, man, there's no shadows. I'm walking, I don't see my shadow on the ground. This is going to be kind of cool. We're going to get a whole day of going down here, walk all the way to the park, and then the teacher's going to realize that we can't do shadows, and then we're going to get a second day to be able to get out of school. And we get down there, and all of a sudden he starts breaking out these little tiny mirrors, and I had no idea what we were going to do. but he was pretty slick. He knew that there was another option if it wasn't sunny outside. So here's kind of the deal. If you have the ground, and this problem talks about a museum, you have the ground, and it says to find the height of a dinosaur in a museum. And man, I'm not even going to attempt to draw a dinosaur. I don't know. This is a really bad dinosaur. Some little T-Rex arms. All right, so bear with me. Maybe some teeth and an eye. But we're trying to figure out the height of that dinosaur. And there's no shadows inside the museum. We're inside. The lighting's not that strong. But what you can do is, as long as you know how tall you are, you can place a mirror on the ground. So you place this little mirror on the ground, and you're standing, over here somewhere. And you move either forward or backward until you get to a point where you can see the very top of that dragon's head in the mirror. And if that happens, once you get to that magic point where you can see that, mirrors work in such a way that your line of vision, whatever it comes in, it goes out. It's called the angle of incidence and the angle of reflection in physics, or it even happens in pool. If I'm playing on a pool table and I shoot a ball and it hits right there, whatever angle this is, it's going to take off at the exact same angle. That's kind of the idea that we're using. So I know that these two triangles are similar because, we kind of have a perpendicular line over here. Hopefully I'm standing straight, that's perpendicular. And since we have two angles that match, the third angle has to. So I now have similar triangles and I can use proportions. So here's what you do. The kid stepped back 4 feet from the mirror. And he is 5 feet 6 inches tall. Now, 6 inches, this time it's going to be helpful for me to convert that into feet. 5 feet 6 inches, well, to change it, I'm going to do 6 inches over 12 inches, which is 0.5, which is half of a foot. So this kid is really 5.5 feet tall. And he's 4 feet away from the mirror. Well, then he measured the distance from the dinosaur on the ground, and it was 40. So that should help me solve for the height of the dinosaur over here using mirrors as opposed to shadows. Still indirect, but same idea. So two ways to do this problem. You could set up a proportion. Height of the kid over distance from the mirror equals height of the dinosaur over distance from the mirror. And you could cross multiply and solve that. There's an easier way though. I could use scale factor. And I see that the dinosaur's distance is exactly 10 times further from the mirror than my distance. So the dinosaur's height should be exactly 10 times the height of the kid, which would put him at 55 feet. It should work the same if you do this. You'll get 220 equals 4h, divide both sides by 4, and you will also get 55 feet if you use the proportion method. Alright, so I tried to give you a decent little sample of problems where you can measure the length or distance of things by using shadows or by using reflections in mirrors. So this lesson is about indirect measurement. So, get your notes done. I will see you tomorrow and we can get after this practice. See you.